Hello everybody, welcome to the last HELYX webinar of this Learn by Example series. My name is Lisandro Maders, I'm the manager of ENGYS Brazilian office, and today's subject is about conjugate heat transfer within HELYX. Today's webinar goals are first to quickly introduce ENGYS and summarize our developments in the CHT area, and then to obtain a sense of how CHT cases can be easily set up within HELYX. Lastly, we will answer all questions post-webinar. So if you have any questions, please simply reply to this webinar email invitation and we will contact you. For those who don't know ENGYS yet, ENGYS is a global provider of CFD products and services since 2009. And because we have highly experienced phone and open phone CFD developers since 1999, we have been able to provide incredible CFD solutions for more than 200 companies. ENGYS has offices in 8 countries and a well-established distributor network around the world. Regarding ENGYS products, we deliver products that join the benefits from both open source and commercial CFD technologies. The main open source benefits I am talking about are full capacity of customization of the source code and free scalability. And that means no HPC licenses are required. So with a single license, the user can run as many simultaneous simulations in as many processors as the user wants. And some of the commercial software benefits I was talking about are an easy-to-use graphical user interface, best-in-class technical support, and an extensive written documentation. And this resulted in the current ENGYS products, which are HELYX, our general-purpose CFD software for enterprise, Elements, an advanced software suite for the automotive industry, and the HELYX add-ons, which are a set of additional modules covering specific applications like adjoint optimization, marine applications, advanced multi-phase flows, and our in-house developed coupled solver. So what is conjugate heat transfer? So basically, we talk about CHT problems when we have heat transfer phenomena occurring on multiple fluid and or solid regions simultaneously. And since they occur simultaneously, we want to couple such physics. And this is done by the energy equation coupling at the interfaces between those regions. In terms of applications, there are several possibilities like heat exchangers, like the example I will do today, data centers to model the servers, engine cooling and battery cooling in the automotive industry, electronics cooling, and the list continues. In terms of CHT functionality in HELYX, as everybody might know, ENGYS has started its developments based on OpenPhone. And in the past 10 years, lots of advancements and improvements were done in the source code. And one great example is our totally refactored CHT solver, which was originally a segregated solver in OpenPhone, and now it's a fully coupled solver in HELYX, in the sense that the energy equations for all the regions are solved in a single monolithic matrix, which we like to call a super matrix. Also, another great example of ENGYS improvements in the source code is the unified solver framework, which the CHT solver is part of. So for those who have already used OpenPhone has more than 100 different solvers, each of them solving a different set of physics. And this results in more than 100 momentum equations, more than 100 continuity equations, dozens of energy equations. And this, of course, results in lots of code duplication and damages maintenance. So in the past years, ENGYS has been refactoring the entire source code in order to get one single solver, which we will call HELYX solves, in which the physics are going to be included in a modular solver building block fashion. And this will add simplicity and maintainability of the source code, easier extensibility for other applications, and of course, the most important for our customers, faster and more relevant CFD innovations delivered to the market. And I brought this subject quickly in this webinar since the CHT solver was one of the first solvers developed in this unified solver framework context. So about the live demonstration, previously in the multi-region meshing webinar, I presented two different approaches for solving multi-region meshes. which is the first step for solving any CHT problem. In that webinar, I meshed a shell tube heat exchanger using the multiple material points approach, but today I'm going to mesh it using the zoning approach. And I will show that with the zoning approach, we have better control of the mesh, even if it requires a bit of surface manipulation. Then I'm going to set up the case, run it, and post-process the results. In terms of the problem description, we have two streams of water, one which is hot and another one which is cold. The cold one has a mass flow rate of 0.2 kilograms per second, a temperature of 24 Celsius degrees. The hot one has a higher mass flow rate with a higher temperature. We are going to apply a convective heat transfer boundary condition in the outer shell surface. And also we are not going to model the tubes as solids, only the plates and the baffles. So for the two tubes, we are going to model its thickness, applying a virtual thickness with a thermal conductivity of 50 watts per meter Kelvin. So let's go to the live demonstration, and I will have to change machines quickly because I am in my laptop Windows machine and I want to change to my Linux machine. So bear with me 1 second, the screen might be black for a few seconds. Here we go. Please let me know if you can still hear me fine or if you cannot hear me fine, because I changed the machines and changed my microphone. So the first thing we need to do is to import our geometry. We do this on this button from File. If you watch the previous webinar, you will notice that this geometry have some surfaces split into more surfaces, like the plates, for example, and the baffles. And this is because of the zoning approach, which is slightly different from the multiple material points approach. Hopefully you will understand this in a second. So let's define the mesh algorithm as the standard one. We are going to select the base mesh size as 32 centimeters. And when talking about multi-region meshes with the zoning approach, I like to start with the material point location. So this is a good material point location for my explanation, so let's use this. And I like to think as if the material points explodes, and when it finds a surface, the mesh algorithm needs to know what to do with such surface, how to interpret it. And as default, it will interpret it as a wall, and that means it will stop meshing. However, there might be some surface that we want to mesh inside it, and this is the case, for example, for the plates and for the baffles, in which we want to have a solid region, solid mesh region. So in order to tell to the mesh algorithm that we want mesh inside the surface, what we need to do is go in the zones tab for the plate 2 underline in surface, and instead of none, we select type internal. And we want more than that. We want also that the mesh algorithm generates a cell zone for this plate. So later we can split this cell zone into a solid region. So in order to do that, we are going to check this option cell zone and give it a name. Awesome. Now we need to tell to the mesh algorithm when to stop generating this cell zone, and we want it to stop generating this cell zone in the surface. So basically what we need to do is to tell it that this is also an internal surface, since we want it to keep generating the mesh after it. Okay, and we need to do this as well for the baffles. So let me do this for the baffle number 1. We need to do the same thing, so we are going to tell to the mesh algorithm to mesh inside the surface, and from this surface on, we want to generate a separate cell zone, so we are going to check this box on and give it a name. And we have those other two surfaces, and both of them will have the same settings as the plate 2 underline out. And we can do this for all our surfaces. So let me select all the surfaces that ends with the underline in. And I'm going to select internal and check the box cells on. And for all surfaces that ends with underline out and wall, I'm going to select internal. Okay. We need to do the same thing for the tubes, because if you think about it, when we have our material point location, it will start meshing inside the tubes, and we also want mesh to be generated outside the tubes, more specifically in between the tubes surfaces and the outer shell surfaces, which is not being shown here right now, because this will be our hot water, right? So what we are going to do is to select tubes, mark as internal, and mark the cell zone. And let me give the name hot region to this new cell zone. And as we did for the other surfaces, we're going to select this surface as internal, because this will be an interface between the solid regions and the fluid regions. Cool. Now we need to select the surface refinement. So I'm going to select all baffles and plates and tubes, and I'm going to apply a surface refinement level of 4. For the inlet and outlet boundary conditions, a surface refinement level of 1, and for the outer shell, a surface refinement level of 3 and 4. Now we need to specify the layers growth. And this is where the zoning approach differs from the multiple material points approach. We can apply layers on a single side of this interface. And that's why I said in the presentation that we have better control of the layer growth using the zoning approach. So when walking from the material point to on, every phase that it finds generally will be on the fluid side in this case, and this will be on the master side of the interface. Okay, so basically we want layers on all master sides so we have layers only on the fluid side. This is kind of a try and error approach, because if you have a too complex geometry in which the material point can reach that surface from both directions, this might change a little bit, but for this case this is enough. So I'm going to select all my solid surfaces, and I'm going to apply 3 layers with a ground ratio of 1.1 and a final layer thickness ratio in relation to the surface refinement cell size of 0.25. And on the layers, on the slave side, I'm not going to apply any layers. And for the tube surfaces, then since this is an interface between for those tubes surfaces, since this is an interface between fluid regions, we want layers on both sides. And here, since this is an interface between a solid and a fluid region, we are fine letting this slave side with no layers. Good, so we are good to go. And if I press the button create mesh, it will start to generate our mesh. Let me stop here, and because it takes a few minutes, and let me open an already done mesh. So this will be the resultant mesh. If we take a look into the mesh settings, we will see that we have the same thing, no layers in the slave side, 3 layers in the master side. For all the underline in surfaces, we have internal as type of the zone, and we have this optional cell zone marked on. And for the out and walls, we simply have the type internal. and also the master with 3 layers and the slave with no layers. Okay, so if we take a look, we have the expected result in terms of mesh. So here we have the tubes, and we have layers on both sides, okay, on the cold side and also in the hot side. But if we look at the baffles, this is the interior of the baffle, so this is a solid, and we don't have layers generated here. We only have layers on the fluid side as expected, right? And here we have some layers collapsing, so in order to overcome that, we could refine a little bit this region here, but for the purpose of the webinar, this is more than enough. So we have a very nice mesh with layers covering most of the surfaces in the fluid side. And one next step that we need to do is to split this mesh, because right now what we have is a single mesh with different cell zones. So if I turn on the baffle 1 cell zone, you will see that this is part of this unique mesh. And we need to split that. And we do this in the Mesh tab, in the button Split Mesh Regions. And here we can split the mesh into different regions, starting from the different cell zones. Okay, and we could drag this around to make a combination that we want. But for our case, this is exactly what we want. So let me click Run. Okay, and the result is now we have a multi-region mesh. So we have different mesh regions. For example, the baffle 1 mesh region. And the baffle 1 mesh region has an interface to the cold region, to the cold water, and also an interface to the hot region. So those two are interfaces automatically generated by the graphical user interface, and this outer shell is simply this patch here, which is a simple patch, not an interface between regions. Okay, for example, for the cold region, which is our default region, we have this default to hot region, which again is an interface between the cold and hot region automatically generated by the graphical user interface. So we are good to set up our case. So in the solution tab, if we have a multi-region mesh, most of the settings are automatic. We can select steady or transient. If buoyancy is important, we can specify the gravity. We don't want air, we want water, and we don't want steel, we want aluminium, and we could add as many materials as we wanted. And let me select aluminium for the solid properties, for the solid regions. Let me just double check, yeah. And for the fluid regions, let me select Calm SST, runs modeling for turbulence. Let me deactivate buoyancy. We could specify radiation if you wanted, but we are not going to do this now. And for the hot region side, the same thing, deactivating buoyancy. Okay, now we need to set up our boundary conditions. So for example, for the baffle number 1, we have this interface, and you can see this is automatically set up, and it finds the patch pair with the cold region, which is actually our default region. So we have this baffle 1 to default interface in the baffle 1 region, which is a patch pair for the default to baffle 1 interface in the default region. And this is automatically recognized by the graphical user interface. Same thing for the interface with the hot region. So in terms of boundary conditions, let's think about the inlets and outlets for the cold and hot side. So for the inlet on the cold side, we want a flow rate of 0.2 kilograms per second with an inlet temperature of 297 Kelvin, which is 24 Celsius degrees. For the turbulence, I will leave the default for all the batches. For the outlet, we simply are going to apply a fixed static pressure. And if we have some backflow, this will apply this temperature here. For the inlet of the hot region, we have a 0.35 kilograms per second flow rate with a temperature of 320 weight, which is 55 Celsius degrees. And for the outlet, we also have fixed static pressure. Cool. Next boundary condition that we have is a convective heat transfer boundary condition in the outer shell surface. So let me select all outer shell surface. And I can multiple select them. And I can select convective heat transfer. And here we can apply is 31 Celsius degrees, which is 304 Kelvin. The convective heat transfer coefficient is 10. We don't want to apply any heat flux on this surface. And we could, if we want, apply, for example, an insulation layer with a specific thickness and a thermal conductivity, but we don't want to do that. Cool. And now, lastly, we are not modeling our tubes as solids, but if we wanted, and we do, to model the thickness of these tubes, we need to select them. So we can choose either in the default region or in the hot region, since they are the same interface. So let me select the default to hot region one. And in the thermal tab, I can select contact resistance. And then I can apply a layer thickness of 2 millimeters with a thermal conductivity of 50 watts per meters Kelvin. And that's it. That's it for this case. So we can skip the cell zone since we don't want to apply, for example, a volumetric heat generation in any of the baffles, but we could if we wanted, okay? Or we can apply heat exchanger models as well and other more advanced options. Numerical schemes and solver settings, those are selected as based on best practices from ENGYS, based on all the options chosen here in the solution section. Okay, so for 90% of the cases, we don't need to change this. Let me select 500 iterations, right on the disk at every 250 iterations. We can apply some monitoring functions. So for example, for the hot region, I want the mean, maximum, and mean values for the selected fields. Let me take out thesis flux since this is a surface field. And we could apply other monitoring functions as well. So for example, surface report on the tubes in order to get the average temperature of the tubes. So we can specify temperature in the fields, and in the phase zones, we can select our tubes, right? Okay, and then lastly, in the initialization, we can initialize everything, all the solids with 300 Kelvin. And for the default region, we can apply a initial dummy velocity. I will leave those options as it is. I will apply the inlet boundary condition value for temperature. And same thing for the hot region. And we are good to go. So if I click initialize, I have my solution initialized and I have everything ready to run the solver. So once I click run solver, I can follow my residuals in this residuals graph, and I also can check my monitoring functions with this graph here. Okay. And of course, since this would take a while, I'm going to stop this and I'm going to open an already done case. So those would be the results that we would get. So here we have some streamlines. So the inlet of the cold side, the cold water is here. Here is the outlet. We can see that it starts with a lower temperature and it gets increased as it moves along the heat exchanger. We have also the hot water inlet and the hot water outlet. And we can see it starts with a higher temperature and leaves the domain with a lower temperature. Also here with the streamlines, we can see easily the reason why we have those baffles. So basically they enhance the mixing of the fluid, and hence they increase the heat transfer efficiency. Also I can go to my scenes, pre-saved scenes, and I can check the temperature contours on all my regions, fluid and solid ones. So here we can check that we have a thermal boundary layer developing as expected, and we can use those results to check our mesh. So of course for this webinar the mesh is okay, but probably we would want more layers to capture properly this thermal boundary layer, right? And maybe as well we want to refine a little bit on this area here in order to capture this wake, since this is temperature contour, but if we look at the velocity, probably we would find some kind of wake here. And that's it. You can check the temperature on the solids, right? Because we are modeling the heat conduction in the solids as well. And basically that's all I wanted to show. Okay, I hope that was clear, and let me go back to the presentation since I think I'm running out of time. So a few take-home messages before we go. The entire idea of this webinar was to show you that HELYX can offer a comprehensive CHT solution. We have a flexible, streamlined workflow to get the job done when we are talking about conjugate heat transfer problems. And also our totally in-house developed CHT solver, which has an implicit inter-region thermal coupling, has a performance which is very comparable to Fluent and other commercial CFD tools. And we had several companies already that replaced other commercial CFD tools by HELYX because of the HELYX CHT functionality. Okay, so this is the end of the Learn by Example series for HELYX. We still have one more Elements webinar. You can check blog.engys.com for all the recordings. And for questions, please, you can leave a message to info@engys.com, or you can simply reply to the email invitation for this webinar. I'd like to thank you a lot for your attention and see you in next webinars.